I'm going to talk about two different subjects. The first part is about creative machines before there were computers. So machines that were made to generate language or music or artwork, and the techniques that people used to do that. And then in part two, I'm going to talk about some new methods that have become available with computers and how we can go beyond the sort of things that people were doing back then. Especially my own research in combining knowledge bases with digital semantic vector spaces. So the two halves of the talk are quite different, and I changed typefaces halfway through. You can tell very easily when one ends in the other. So in 1817, Sir David Brewster invented the kaleidoscope. Other people before that had noticed that if you put two mirrors at an angle, that you can get symmetric patterns. But he was the first one to build the two kaleidoscopes that we understand now. And it was a huge hit. It became the fad of London. He wrote to his wife, "You can form no conception of the effect which the instrument excited in London. All that you've heard falls infinitely short of the reality. No book and no instrument in the memory of man ever produced such a singular effect. They're exhibited publicly on the streets for a penny, and I had the pleasure of paying this sum yesterday. These are about 2 feet long and a foot wide. Infants are seen carrying them in their hands, the coachmen on their boxes are busy using them, and thousands of poor people make their bread by making and selling them." When Brewster invented it, he intended it as a kind of labor-saving device for artists, not as a toy particularly. He said there's few devices that can so easily do what a person does, but 1,000 times faster. So they were at the time, many artists were employed in making symmetrical patterns for the covers of books or to decorate buildings. And I think partly because of the invention of the kaleidoscope, that making that kind of patterns fell out of favor. That once people realized that the process could be automated, it changed our ideas of what made something artwork. But the kaleidoscope forms a kind of pattern that we're going to see over and over again in the other devices described here. First off, you have some beautiful elements, maybe the beads or colorful pieces of glass at the end of the kaleidoscope. Second, you have some sort of rule for combining them. In this case, the symmetry of the mirrors. And the third thing, and that rule imposes some order on it, and we perceive the finished product as beautiful because it follows these rules. The third thing is it has some sort of source of randomization. So these different devices all follow that same plan, where they do some randomization, they have some order, they have some beautiful pieces that they're rearranged. Here's the quote about how the kaleidoscope was useful. "When we consider that in this busy island thousands of individuals are wholly occupied with composition of symmetrical designs, and there is scarcely any profession into which these designs cannot enter as a necessary part, so as to employ a portion of the time of every artist, we shall not hesitate in admitting that an instrument must have no small degree of utility which abridges the labor of so many individuals. There are few machines indeed which rise higher above the operations of human skill. It will create in a single hour what 1,000 artists could not invent in the course of a year. And while it works with such unexampled rapidity, it works also with a corresponding beauty and precision." This is from Brewster's book about the kaleidoscope. So the kaleidoscope was an early example, but by far the earliest example we have of generating new artwork, new ideas from rules is something that is called geomancy. So if you think about what the very first computation device was, the first device that somebody created to help them to do mathematics, it was probably a box drawn on the ground with his stick and some pebbles. And those pebbles and blocks form kind of a external memory where the person using the pebbles was able to keep track of the numbers, and other people could verify that he wasn't cheating when he says, okay, I'm taking this many sheep and giving it to you. And that idea of representing concepts as an external representation probably gave rise to the thought that this could generate new ideas rather than simply representing ideas that were already held. And so for geomancy, maybe you would drag a stick along the ground and it would hop up and down randomly as it moved along. And looking at the pattern that it formed, you would recognize, okay, this pattern is populous, this pattern is Fortuna minor, and from that you would put together a fortune. You would tell the answer to a question that someone was asking. Now, of course, the answer that this is generating has almost nothing to do with the question that's input. But for thousands of years, all throughout the Middle East and Africa, people were using these techniques and being satisfied with it. So it makes us, we should be a little bit wary when we make artificial intelligence techniques that are convincing to people, right? That's the definition of passing the Turing test, that you can convince people that this is a thinking being. Because people were doing that in 2000 BC, right? Convincing people that a machine was generating new ideas. Just convincing people maybe isn't enough for actual cognition. Here's another version of the device now built out of brass. You can see this inscription above the dial. Those are the same patterns that we saw before. And the inscription says, I am the revealer of secrets. So it's personifying the machine and saying, I will tell you the answer to your questions that you pose.
Is it AM or FM? I mean, it really shares a lot with the designs of the radio that came in later.
Here's a new, another device. This one's called the Eureka. And this is a device for generating music. So the Eureka, well, in the 1830s and for hundreds of years before that, one of the assignments that they would give to school children was to create lines of Latin poetry in the hexameter that was used in the Iliad. So writing these poems was something everybody was familiar with. And at some point in the 1600s, they published a technique that you could use to automatically generate as many of these as you wanted. You could always follow the same grammatical structure for your 6 words, where you have adjective, noun, verb, adjective, noun, or something like that. And the constraint of the meter would also be imposed on those words. So by picking a word randomly from each of these lists, you could compose a new line of poetry which was both grammatically and metrically correct. And in 1830, John Clark built a machine that would do that. As it generated these lines of poetry, it would also play God Save the Queen on a music box and make a new kaleidoscope image display. So I put a lot of effort and the 3D modeling program, Bryce, if you've ever used that old ray tracer, to make this. This is a illustration of how the interior of the mechanism works. So you have these barrels, one for each word, and the height of these pegs, as it goes up and down, encodes the letters of the word that are being spelled out. And it'll spin around randomly to a new angle. And then these wedges drop down and depending on the height, the wedges are able to drop to a greater or lesser distance. And he deliberately did this to trick people who are watching the machine. Because as you watch it, instead of looking like it's coming up with one word at a time, it looks like individual letters are coming down one at a time, and that it's spelling it by words. And we have a letter to the editor where he defends his machine, saying, no, it's not composing word by word. It's using mathematical techniques to make words up letter by letter. So here's the animation. You can see the barrels spin around, and it turns around. It's actually playing God Save the Queen, but we have to turn it off for the feedback. Inscribed on this, it says, eternal truths of character sublime, conceived in darkness, here shall be unrolled. The mystery of number and of time is here displayed in characters of gold. Transcribe each line composed by this machine. Record the fleeting thoughts as they arise. A line once lost will ne'er again be seen. A thought once flown perhaps forever flies. So the thought is that this could generate new poems, and if you didn't write it down, no one would ever see that poem again. William Thackeray, joking for Punch magazine, said several double-barreled Eurekas were ordered for Eton, Harrow, and Rugby, the schools, so that they could churn out as many of these poems as they needed. The economist William Hodgson wrote, "It is truly a curious machine. Though I cannot say much for the sense of the verses, the inventor spent 15 years upon it, 5 years more than are needed to make a boy into a verse-making machine, and still less perfect. Clark is a strange, simple-looking old man. Babbage said the other day he was as great a curiosity as this machine." This idea of doing random recombination of terms was used earlier by Raymond Lull in the 1200s. He wrote the Ars Magna, and the Ars Magna was an attempt to generate new arguments for the existence of God especially. And in the book, he has these on paper dials that you can turn around. It's like a pop-up book. And you can prove, well, suppose somebody believes that anything that is great in magnitude is good. And believes that anything that is good is virtuous. So by establishing a few of these points that they already believe, you can then prove that these other facts must also be true about God, and so all these facts are true about God. And he convinced himself that this was a really useful tool, and that it could go about convincing anyone of the things he believed about God. And so he went off to convert the Muslims, and probably got himself beheaded. Could hear the Aeolian harp. This was, well, you've all seen wind chimes. Wind chimes generate a kind of melody as the wind blows them, and different notes are played. On the left, you have a musical kite that they fly at celebrations in China. And as the wind blows through these, it makes different tones. Here in the large image shows an Aeolian harp. And as the wind blows across the strings, it sets them vibrating. Coleridge called it a vast floating witchery of sound, a really alien kind of sound. And this was referred to as the Romantics scientific instrument. That this was how they understood nature creating artwork. That each of us was a Aeolian harp of a kind, being animated by the forces of nature, and in that way creating. Here's his poem about it. Coleridge writes, "And many idle flitting fantasies traverse my indolent and passive brain, as wild and various as the random gales that swell and flutter on the subject loop. And what if all animated nature be but organic hearts diversely framed, that tremble into thought, as o'er them sweeps plastic and vast one intellectual breeze, at once the soul of each and God of all. Mozart also invented a way of generating music. And in this, you would roll dice to choose which from among a table of measures would be played, and then roll again for the next set of measures. And you can actually use this now to hear a Mozart composition that nobody else has ever heard before, if you want to. And along the same lines, we have the Componium by DeepDream. Winkel was an inventor in Amsterdam in 1821. He was a recluse, stayed at home all the time, but was a very clever inventor. And another inventor at the same time, whose name was Maelzel, was much more outgoing. And he would travel around Europe showing off his inventions. He bought the Mechanical Turk, which is a chess-playing automaton, supposedly, but it's actually a fraud. Someone's hiding inside operating the levers. And everything Maelzel did was tinged with this fraud. He was as much a showman as he was an inventor. Anyway, he visited Winkel at his house and said, "Oh, I'm such an admirer. Show me your latest invention." And Winkel showed him a metronome that he had invented, which is the same metronome that we use today. And Maelzel had also invented a metronome, but it wasn't nearly as good. And so Winkel's metronome was promptly stolen by Maelzel. He marketed it all over Europe. We still call that metronome Maelzel's metronome. And a lot of what we know about Winkel is from the lawsuit that he filed, saying this is my invention. Anyway, another invention, the one that Maelzel was most proud of, was that he'd made an orchestrion, a music box that would play from horns and drums and flutes, all playing at the same time, an orchestra automatically. And Winkel thought, I can outdo that. So what he invented was this Componium. And just like Maelzel's, when you turn it on, it would play a tune. But then, after it finished, it would start improvising on the tune and play a new improvised melody based on the tune that it had just played. The way that it was able to do this was these barrels here each contained multiple versions of each pair of measures. And so it would play through that one version of the measure, and then had a random spinner that would, like a loose band that would disengage and let it spin randomly and then engage again. And so it could choose a different tone for the next section of the song. And so he was able to outdo Maelzel with his actually composing the music as it went along. It was very impressive to the people who went to go see it at the for a shilling in London. They said, already mechanical science has succeeded in binding down the wings of genius, and carpet manufacturers and fancy workers no longer consult the tastes of artists, but apply to the kaleidoscope to supply them with new patterns. Are musical composers in future to be taught to take their inspiration from such an instrument as is now exhibiting? So these are all generative systems that they come up with new material from what they're supplying. And in the 1800s, they also started to find ways of automating logic. So here we have a logical piano built by Stanley Jones, the economist. You would input something like A equals AB, meaning that A implies B, and maybe A equals AC, so A implies C. And then it would tell you all of the possible combinations of A, B, C, and D in which those facts were true. So you could have A, B, C, and not B, but you couldn't have A, not B, C, D. And John Venn said, well, okay, that's great, but you're missing most of the important parts of solving logical problems. First, you need to state your statement in the language of data. And then you need to throw those statements into a form fit for the engine to work with. Third, there's the combination or further treatment of our premises after such reduction. And finally, the results have to be interpreted or read on. So kind of what he's proposing here is making programming languages and a compiler, right? That the hard part is interpreting the English language and turning it into a form that the computer is able to work with. In 1832, Simon Korsakov built something that I think people here at Google would especially appreciate. It was the first search engine. He was a policeman for the Russian police, which even in those Tsarist times was a vast bureaucracy. And they collected information on every person in the district. And he invented a machine that would enable them to search through all of those records to find someone who met certain characteristics. So what it did was that it had holes punched out for all of the facts that were true about a person. Maybe their hair color, their eye color, their age, and so forth. And then it would run this this rotating set of pins across each page. And when the pins were able to fall through all of the holes at the same time, the paper would slip down over the pins and be pulled out. But otherwise, the pins would not catch on the paper. And so he was able to automatically select from this set of punch cards. He open sourced the documents. He showed it to the Russian Academy. They didn't care. Today, Semyon Korsakov is remembered more for his homeopathic remedies than for his inventions. But he wrote, machinists, intellectuals would limitlessly strengthen the power of our thoughts. As soon as distinguished scientists apply their knowledge to studying the principles of this process and compose the tables necessary for its application in various fields of human knowledge. So visual arts also, you have some techniques. So the Japanese wanted natural forms in their artwork. On the left, you would drop oil paint on water and press a piece of paper across it and lift up the pattern. So the naturally generated forms look like wood grain. And the raku pottery, the different temperatures, the mixture of the glaze would create different patterns that the artist didn't intend exactly what it would look like. He wanted the natural processes to get to affect it. Here's some similar examples. Jared Tarbell has created the program on the upper left, which uses techniques similar to city generation in games to lay out these patterns. Tim Knowles taped markers to the bottom of a weeping willow, and as the wind blows, it makes random patterns on the paper. So all of these machines, they all share those same source of randomness, the generated elements, source of order, and they use the same technique basically to recombine these pieces. And so today, when people do generative art, this is the first thing that occurs to them, to follow the same thing. But we've got a lot more powerful techniques that are available to us now, and hopefully we can come up with things that exhibit more attributes of creativity. This is image analogies, which was created by Ann Hertzman at NYU. And when I was at NYU, I used this to make a image super resolution algorithm. Basically, what you do is supply 3 images: the photograph on the upper left, a painting version of it, and then the photograph that you want to convert. And it finds tiny patches of the photograph on the upper left and matches those patches to similar patches in the lower left. And so copies the similar patch from the upper right to the lower right and creates an image in that style. It also makes an effort for the patches that are to match up at the edges so that it's smooth. Similarly, you can create on the left the plan that you want to go with the image, and then create a new plan and generate a new version of the target. More recently, some people have.
You're saying the bottom right image is just completely hallucinated?
That's right. It's generated from patches of the image on the upper right, rearranged according to the correspondence between the left images.
Is it just working with patches?
That's
Small
right.
patches?
Yeah, small
I'm
patches.
wondering how you got the effect of on the water. You see this lighting effect that it's even brighter at the top than at the bottom.
Yeah, well, here you see this.
Oh, I see. The
red is
gradients
the same
are
color,
yeah,
so it's a
okay,
gray
got it,
thing.
yeah, okay. That's cool.
Now we have ways to do this without the same image, three images, where you're able to take a correlation between features in a deep neural network and use that to create an image in the style of another painting. So this is starting to learn from images. It's starting to pick up elements of style that we can't characterize exactly. This is Parade Loop by Phil McCarthy. Pareidolia is the tendency to see faces in clouds or in tree stumps. Here, the system randomly places triangles on top of each other, but it has a face recognizer, an image recognition system. And when it sees something that looks like the face, it keeps that and keeps working on it and keeps going back to the best detection that it's had and tries to improve the quality of the face detection. So this feedback effect, where you're able to observe what you're creating and modify it to make it look more like what you are trying to imagine, that's an important part of creativity, which you see in the DeepDream developed at Google. A friend of mine at work used some of the tools that people have put out there and generated this from the image on the lower right. It hallucinated this image on the upper left. You see there's a lot of dogs' faces in there. That's because the training set contains far too many pictures of dogs.
No, we're dog campus, not cat campus.
But again, with the DeepDream software, it looks at the image and it tries to recognize objects in the image. And when it pulls out an object that's being recognized, it enhances whatever it's causing it to be seen. So brings out the images that are implicitly there. But all of these systems fail at some of the things that we really want our artists to do. That they don't seem to understand what they're doing. And understanding, it's a loaded word. But as a teacher, as a school teacher, we had pretty specific tests to know whether a student was understanding something. If they could summarize what they'd seen, if they could interpret it, compare two versions of it, answer questions about it, or integrate it with other knowledge that they had, then that showed that the student had understanding of the concept rather than just rote memorization. So that is the sort of thing that I'm trying to build into the system I'm going to describe, the ability to exhibit these attributes of understanding. So a knowledge base is one way that people try to encode understanding, that every object it exists in this knowledge graph and has labeled links to other objects in the graph. So an automobile is a type of road vehicle, which is a type of transportation device. And then there's other things like the orange link have other meanings, like an automobile is found in a garage or lives in a garage. So you have this ontology, named relations between the contexts, and then an engine for performing deductive reasoning on these facts. So knowledge bases were going to be artificial intelligence all through the 80s. But eventually people realized that they had some pretty significant flaws. So one of the things is you need to encode everything that you want to say in the language that the knowledge base understands. This is an example of saying a thermos is capable of holding a liquid, so you can ask the question, putting in a variable, what is capable of holding a liquid, and it should return thermos. You can also use other logical connectives. So what is capable of holding a liquid and is not a container. And for my PhD thesis, I built a system which took scenes and used scene labeling techniques to recognize what all of the objects were in the image, and then constructed a kind of 3D map of the things that were in the scene, and then placed assertions in the knowledge base about what objects were found. So saying things like there's a tree in the image. The tree is next to a building. And then there were facts in the knowledge base that it could reason about these. So you could ask a question like, is there anything breakable in the image? And it would say, well, there is a car in the image, and cars always have windows, and windows are made of glass, and glass is breakable. So yes, there is something breakable in the image. You were able to ask questions about the things that were being seen. Which made me think about how children create artwork themselves. So here we have an image on the upper right of the sort that my program was able to recognize the objects in. And on the other sections of the image, you can see children's drawings of what they see in this picture. These are the youngest children, the 4-year-olds. And what you'll notice, if you look at this, is that what the children are drawing has almost nothing to do with what you see in the image in terms of the layout of the shape. Instead, they've recognized objects in the image, and they've used the script that they have in their head for how to draw those objects. So these children know how to draw a building. A building is a rectangle with a triangle on top of it, with a door in it. And so they use that to represent the building. The road, with its markings, is not drawn from the perspective you're actually seeing in the image, but is turned so that it's a way that you could have a road. Older children begin to incorporate some of what they're seeing, but there's some weird contradictions. So here Nini has tried to draw. Sorry, I don't know how to. Maybe that's you?
On the touch screen.
On that phone.
Oh. Okay. Here, Nini's tried to draw a car. I don't know what it is.
We're just going to chat him and tell him to come in with his crayon.
Yeah, in the room. I don't think there's room.
He's in Seattle.
Oh.
He's on my team, so I can ping him, and I think he tried to use. I think he tried to.
Anyway, she knew there were 4 round wheels on the car, and so she had to draw those 4 wheels as circles. But there was no way to fit it on the way she'd drawn it, so they're just randomly sticking off the sides of the car. The buildings here on the right, he knows that they're supposed to be perpendicular to the road, but in 2 dimensions, how is that perpendicular supposed to go? So the point behind this is that these children are not drawing what they see. They're seeing something, they are understanding it, representing it as concepts, and then creating those concepts on the paper. The older children, the 10 and 11-year-olds, began to be able to use perspective, but still are making mistakes based on what they have preconceived. So this was an add-on to that program that I built. it would look at the image on the left, create the scene labeling you see in the center, and then say, okay, this green area, that's buildings. So I'm going to place some template drawings of buildings in the scene. This is a road in purple, so I'll place a road there. And it's a very, very simple way of making a drawing. But the nice thing about it was it could answer these questions. What is on the left? What are the buildings made of? What are some of the parts of buildings? What lives in trees? Summarize the scene. These are the sorts of things that you could pose to the system and have it answer about the images. But like I said, there's some big problems with knowledge bases. They're written. If one statement is missing that you need in the chain of reasoning, it breaks and you get nothing. They're created by hand rather than from big data. So they take enormous amounts of labor, and it's hard to know how much labor you're going to have to do in order to make it useful. They're always incomplete. They don't use natural language. And they can't handle spatial reasoning very well. So these are some reasons that knowledge bases never really took off. But in the last few years, semantic vector spaces have started to be used, and those have a great deal of information contained in them implicitly. So you can see this is a projection into 3 dimensions of a 300-dimensional vector space called word2vec. And words that are similar to each other are close together in this space. So there's clumps of words that have similar meanings. Here's another example projected into 5 dimensions with color and size of the dots. You can see a lot of structure in there. But besides this structure of similar words being grouped together, there's some really amazing properties that these vector spaces have. On the upper left, you can see the words man, woman, uncle, aunt. And the interesting thing about these vector spaces is that words which are analogous to each other are related with a geometric structure. There's a parallelogram between them. So that if you take the vector from man to woman and you apply it to the word uncle, add it to the word uncle, the end of the vector is going to be very close to the word aunt. And this works for all kinds of different relationships between words. So singular to plural, different forms of the verb, all exhibit this parallel structure. The relationship between different countries and their capitals are all approximately parallel. You can add together terms, which is the combination of 2 of them. So Czech plus currency gives you some terms which are similar to the Czech currency, the capital of Vietnam, the German Airlines. And this parallel property lets you solve these analogy problems. So Paris minus France plus Italy equals Rome, approximately. It's the nearest neighbor that you're able to find in this semantic space.
By the way, this stuff that came out of Google. Right?
Yes, that's right. Word2vec was invented here at Google. They were able to use a vast corpus of like all of the New York Times data for the last 100 years to train this with the new techniques that they developed here. So
it was incremental update, so you didn't have to hold the whole corpus in memory while you were doing it.
Right. So this idea of doing analogies, it seems kind of like, well, that's a useful trick if you're trying to solve SAT problems, but not so much in the real world. But Douglas Hofstadter has written several books, a little bit if you go to lecture blog, but mostly in his later books, about how analogy is really the central idea in cognition. That when we understand something, when we see something new, we always understand it by analogy with things that we've experienced before. And that this flexibility of understanding concepts by analogy really is what makes people able to form poetic connections, to understand situations which aren't precisely encoded by rules that we've already learned. Here's a nice quote about it. Each concept in our minds owes its existence to a long succession of analogies made unconsciously over many years, initially giving birth to the concept and continuing to enrich it over the course of our lifetime. Furthermore, at every moment of our lives, our concepts are selectively triggered by analogies that our brain makes without let-up, in an effort to make sense of the new and unknown in terms of the old and known. The human ability to make analogies lies at the root of all our concepts, and our concepts are selectively evoked by analogies. In a word, we wish to show that analogy is the fuel and fire of thinking. An analogy, in the original meaning of the word, is a proportion. The proportion they're talking about is something like 3 is to 4 as 6 is to 8, right? That those numbers have the same relationship, I think. The quantity that's trying to be optimized as you build word2vec is similarly that kind of a relationship, where the probability of finding a particular word in the context of king divided by the probability of finding that word in the context of queen is approximately the same as the probability of finding it in the context of man divided by the context of woman. And following through this mathematics, you can see that this is equivalent to the function that they're actually trying to minimize as they create this this vector space. One of the interesting things about these vector spaces is that many of the operations you can think of doing on them will give you the same result. So if you add 2 vectors, or you take the average of 2 vectors, or you take the average of them and you multiply it by some large n, you'll still get the same results out. If you take the element-wise maximum or the element-wise minimum, either one is still going to give you something that has attributes of both of the terms that you're averaging. Because some of the elements of the vector will come from the first vector you're putting in, and some will come from the second vector you're putting in. And so it's very robust to these different operations that you're doing. A vector is somehow composed of the meanings of the vectors that go into it. So this can actually be used for creating poetry. Poetry in a loose sense. To create these, I took a list of adjectives that started with A and a list of nouns that started with A, and took every possible combination of those and put it into the word2vec vector space. And then I put in the word on the left as my input, and I said, find the nearest neighbors of this. So what you're seeing is the nearest neighbor to the word robot in the vector space of only AA words. So a robot is an anthropomorphic automaton. A songbird is an arboreal artist. Storybook, amazing adventure. Look at the word divide, antagonistic arithmetic. So it's combining both meanings of the word divide here, right? It's somehow captures some of the concept of the word divide, and it's using a poetic play on words to represent it. Here's some more of the same using chemistry terms. So chemistry is academic alchemy. Chemists are atomic astronomers. The word neon, amber ambiance. Neon, if you put electricity through it, doesn't actually glow amber, but our idea of a neon sign is what's captured in the newspaper text about neon. So that's the kind of thing that shows up.
These are handpicked, or these were
these were, I'll say they're among the top 5 results that come back. I'm not sure that they're all at the very top one, but I didn't need to go through and select the best. Here it's done some movie reviews. So I put in the word Lost Ark, and it came up and said, what is the nearest noun to Lost Ark, the nearest very common noun? And the most common noun it came up with is movie. And then I said, what adjective, if you averaged it together with the word movie, would be closest to Lost Ark? It said whip-cracking movie. So if you keep going, it says the archaeologist, adventurer, screwball comedies, schlock horror, crystal skull flame, Marion Ravenwood whip cracking movie. That's its description of the word Lost Ark as you keep following this process out. Star Wars, the prequel trilogy, science fiction, lightsabers, toy line, Star Wars.com prequels, sci-fi, lightsabers. So something of the concept that we have for these movies is encoded in the vector represented. Another thing that I attempted with this was to make these dimensions meaningful. So those 300 dimensions, if you try to ask what does this dimension represent, it's nonsense. It's not close to any cluster of words. But you can reproject this vector space into whatever basis you want. So you can choose the vectors that you want to be the basis of this, so that each of them is meaningful. Say a set of adjectives and their antonyms as the two ends of each vector. And as long as you guarantee that the vectors you're choosing are approximately orthogonal, and throw out the ones that are too parallel to something else, and adjust the rest so they're actually orthogonal, you can reproject into this new basis and have the individual elements of the vector space represent something of the meaning of the word. And when you do that, you get something like the Thing Explainer Dictionary by Randall Munro, where you can define a term in terms of maybe the 300 simplest English words that would explain that term, right? The more activated each element of the vector is, the more that word would show up in the definition. So here's how you can use that semantic vector space together with the knowledge base to get out new ideas that aren't contained in the knowledge base. Here's a kind of metaphorical drawing where you have a knowledge base which is like a subway map, and it's got a few cities, a few stops marked out in the subway map. And you know always you can get from this stop to that stop by following the map. But it's not accurate to scale, and it is missing many of the places you'd want to go on the map. On the right, you have a handmade map, and that has many, many more terms in it. But it's more approximate. You're never quite sure how to get from one place to another, and you can't be absolutely sure that everything's accurate on it. So this program that I've written called Displacer uses both of these methods, the knowledge base and the semantic vector space, to enable you to get from any spot in the vector space by use of the knowledge base to where you want to go. And here's an example of how it works. So in the psych knowledge base, we've got many concepts represented and relationships between them, but nowhere near as many as we'd like to have, as many things as we want to represent. In the center, we have the English word strings, and on the right, the vector space. So the question I want to ask is, what are the parts of a backhoe? In the knowledge base, we don't have that information. It has the parts of many machines represented, but it doesn't have the parts of a backhoe. It has the term backhoe, but that's all. So you put in the English word backhoe, and you convert it using word2vec to the digital 300-dimensional vector space, and find the nearest neighbors to it. So the nearest neighbors are identified for backhoe, for dump truck, for shovel. And then take those back into English, and from English into the knowledge base, because the knowledge base knows what English terms correspond to each constant in the knowledge base. And then you ask the question, physical parts of these objects are blank. And it comes up with engines are parts of dump trucks, wheels are parts of dump trucks, shovel blades are parts of shovels. It doesn't come up with any answers for backhoe because it doesn't have any of that information into it. Then it maps that back into English and then into the vector space And now we have a vector for engine and wheel and blade. And now we're able to do that analogy. We have the vectors for the objects, the machines, and we have the vectors for the parts. And so we're able to say, what on a backhoe corresponds to the blade of a shovel? And the answer it comes up with is the excavator. Well, you can't see that. It's hidden under the faces. But what on a backhoe corresponds to the wheels of a truck? It says the tracks correspond. So by forming these analogies, we're able to find facts about the world that were never entered by hand into the knowledge base. And we're able to do that at query time. So when we have a query, we go out and we say, what are the similar terms? What are the answers we can find about those similar terms? And then how can we find the analogical answer for what we actually want to know? Some of the results that we found, in WordNet, there's 346 machines named. Of these, research site recognized 199 of them. And many of those don't have any part information. If we add in semantic matching, we're able to find 294 names of machines that are similar in meaning. When we go to find the parts of those machines, only 39% of those are actually correctly the parts of those machines. But if we use displacement, where it's forming analogies, we're able to set that up to 60% correct names. Another example from the US Census, I found 800 male and 800 female most common names. And in the knowledge base, it has listed famous people who happen to have some of those names. It knew only 37 female names, for example, and 6 of them it male names. But using Displacer, we were able to correctly recognize the gender of 90% of the names. And it might even be higher than 90% because sometimes men and women have the same names. Also, we only used US names, so it might be different in the world. Another thing that we can do is estimate the probability that the analogical guesses are correct. So we're able to say, what is the capital city of a country? And for some of those, we actually know what the answer is. So we say, when we try to estimate this based on the capital cities of other countries, how accurate is our result? And then we can apply that probability to another country that we don't actually know. So one of the facts it had in the knowledge base was that it didn't have was that Berlin was the capital of Germany, because Psych is such an old project that it was still West Germany and East Germany. But it was able to correctly estimate that Berlin is the capital of Germany because it was able to form these analogies from other similar terms. One thing you'll notice from this list, and nobody's ever tried to optimize this, so don't pay too much attention to how good this quality is. But animal type makes sound type, like cow says moo, dog says woof. This sort of thing it did terrible at, because that's not information that shows up in the newspaper very often. Also, a surprising result was I wanted to see how many neighbors you would need to average to find this. And the interesting thing is that there's the lowest distance from the true answer, the best estimate, comes from a very few nearby neighbors. If you average the 4 or 5 nearest neighbors' results, you get the best estimate of the true answer. As you go out farther, the analogies are more stretched, less similar, and so you start losing information. So that means there's less computation. It can be done faster, which is nice. So that concludes the presentation. This is a new system that I think will enable us to do many of the things that we want to do with knowledge bases, but to do it even in cases where the knowledge base is incomplete. This is my book. If you're interested in the first half of the talk, you can get that book on Amazon. The 2 papers listed here, the top one is coming out this November. which is talking about displays or the program I described at the end. And my thesis describes what we have in the middle. So that concludes my talk. If anybody has any questions, I'd be happy to.
There's a meeting at 3 in here, so we'll have to go to the micro kitchen to follow up. Thanks to everyone for attending.